Hello, welcome to this little video lesson. I hope to keep it fairly short, but I just want to review what we went over last class, show you guys a few other things, maybe dealing with some more calculation and how do you actually work with this thing. So if you remember, right, last class we talked about uniform circular motion. We went over an example where, why did that happen? So we went over this example where the net force was non-zero. Oh, wow. It keeps jumping all the way down here. So the net force is not zero, which we concluded because of that, linear momentum was conserved, but angular momentum was conserved. And we saw that a few different ways, but then we moved on to this uniform linear motion example. In this case, F net was zero, right? And namely also because F net was zero, net torque was zero. And we sort of reasoned, we didn't realize how important net torque was at the time, right? So we used some other kind of reasoning to say, whether or not P was conserved, which it clearly is, right? If you just look at the vectors. But then we also calculated sort of using these different R vectors over here, and we actually showed that angular momentum was conserved as well, right? And in our last example, this is where we kind of saw the actual connection between like what specifically causes L to be conserved, angular momentum to be conserved. And this was really kind of the piece de resistance, right? So basically, if there's a non-zero net force, linear momentum is not conserved. We already knew that. Then we discovered, right, if the net torque is not zero, that's what causes angular momentum to not be conserved, right? And we actually walked through all the calculations, and we basically came up with, this is what one of the worksheets called, which I guess we can use this name, the impulse momentum theorem. You don't have to call it that, but essentially we figured out there's an angular version of the one we already knew before, right? So change in momentum is F net times delta T. This is just the rotational counterpart, right? So you have net torque times delta T is change in angular momentum. So that was really neat, right? And essentially this is what we actually look at to determine if it's conserved or not, and also how to calculate the change in the angular momentum. And one thing I'm trying to draw y'all's attention to in this video is that it's really not as important to say, well, what is the initial momentum? What is the final momentum? Because yes, we can calculate that, but really what matters is the change. Is momentum changing? And then how big is that change? And I want to show y'all a quick example in a second here that's going to highlight that. And we also went over this little diagram. I told you guys to write this in your notes because it sort of shows you all the patterns from pretty much everything we have learned in AP Physics 1 so far, right? If you start all the way with linear kinematics, you can use those to derive all the rotational ones. And then we also went this way. If you multiply everything by mass, you get all your momentum equations. And if you multiply all the momentum equations by r sine theta, you get the angular momentum equations. And we also saw that if you take your rotational kinematics over here, multiply by the rotational inertia, I, you get these things, right? And namely, by looking at this very last equation and this equation over here, you realize, oh, well, if net torque times time is change in angular momentum, and if net torque times time is whatever this thing is, I times change in omega, the only possible conclusion you could draw is to say that delta L has to be equal to this I times change in omega. And here I've written it a little differently because, right, so this assumes that I is constant, which we're going to see some problems later on where I changes. in the motion of the object. And so this is actually the better way to write, the combination of those two equations. So we basically discovered, right, there's this alternative way to calculate angular momentum. Angular momentum is the rotational inertia times the rotational velocity, right? We started with this definition. This is just another way to calculate it. And now we have this totally second way of calculating it. And basically, it's just contextual. Depending on what problem you're working on, for problems involving extended objects, so that's when we're talking about like disks, right? Solid disks that are rotating about some sort of center, right? We would want to use this equation. If we're just talking about a particle that's sort of flying through the air at some velocity, and we have some sort of center of rotation, right? And so this would be, we call this the position vector, this guy right here, r, and this would be theta, right? We would just want to calculate L equals mvr sine of theta. So essentially, if you're dealing with single objects, namely things like particles, right, or point masses, in general, you want to use this equation. Anything that's sort of solid, three-dimensional, right? So cylinders, we could talk about hoops, right? So spinning hoops. Those are what we call extended objects, and so we typically want to use this. But I'm going to show you in a second, they actually are both, they're both perfectly valid. You can actually use either equation on any example, basically. And I think we also checked, right, does this actually make sense that these are equal? If you check the units, you realize that they match on either side. So that's pretty sweet. Okay, enough reviewing, right? Let's get into the nitty-gritty here. And, of course, yeah, we talked about the direction, right? So this would counterclockwise, I'll call it CCW. This is when L is positive, right? You use the right-hand rule, basically, to determine that. And then over here, for clockwise motion, this is when L would be negative, right? So, again, right-hand rule. And you can do the same rule with particles as well, which we're going to see in a second. Okay, so now, if you've already seen this sort of thing before in class, potentially literally yesterday, I've actually thrown some twists in here. So we're actually going to do some real calculations, but I want you to notice that this group of particles over here versus this group of particles over here, they're actually just translations of each other. Like I literally copy pasted the same particles with the same velocity vectors over on the right-hand side. The only thing I've changed between these two examples are the centers, right? So in this case, here's my center here. Let me use an X for the center because that's what I've been doing. All right, so the centers have been moved, and the center is what determines how you calculate your angular momentum. So let's do an example here. So L1 in this example. So we would focus on this particle, right? So what would the vector look like? See, that doesn't show up too well. Let me try yellow. Okay, so this right here, this would be my position vector, right? My angle is 90 degrees, right? The 3 is my velocity, and the 2 kilograms my mass, right? So I would just do m, 2 kilograms times v, 3 meters per second, times r. The distance is 2, right? Just going based off of the coordinate system. Sine of theta, this would be sine of 90. And one thing, since this is the first time we've really been calculating with this, there's actually other thing you have to incorporate yourself, which is the direction of the vector, right? So if I do the right-hand rule for this example, my angular momentum should be negative, right? If you actually take your right hand right now, you put your fingers along the r vector and you curl them in the direction of your velocity. Your thumb should be pointing into the screen right now. Right? So if you realize what the direction should be, you should put a minus sign there if it's supposed to be negative. Or you have to put a plus there if it's positive. So you've got to incorporate that. That's actually not necessarily in the formula, right? So you got to make sure to put that there. So we have 2 times 3 times 2, which is 12. And then sine of 90 equal to 1, right? So my angular momentum would be negative 12. Let's see, what would the units be here? That would be kilograms times meters squared over seconds, right? So linear momentum, this was actually just meters, right? But in angular momentum, because we have that times r, we're going to get meters squared, right? So here, let's go over here, take the exact same mass, that was mass number 1. Notice it's all the way up here, right? So I would draw my position vector. Oh, whoops. Whoops. Okay. So draw my position vector. It's r. And I actually have an angle here, so let's just call that theta 1. In fact, we should probably label this r1 because it's the first mass. And so if I want to calculate angular momentum of object 1, I would take 2 kilograms times the velocity times the r, which in this case, I'm going to do a trick here, right? I'm just going to leave this as r1 and then sine of theta 1. Because look at this. We got a right triangle. And you can actually always do this trick if you're dealing with a particle moving in a straight line. And as long as angular momentum is conserved, this should work. This is a distance of 5 meters. And notice we have r1 sine of theta. Well, right? Sine of theta 1 equals 5 over r1. Solve for, what we want. r1 sine of theta 1 equals 5. Some of y'all might have saw that a little quicker, but I just wanted to show that this is true. So when I go down here, this is 5, right? 5, this would be 5 meters, right? That would be the units. And so we get 2 times 3 times 5, which is 30 kilograms times meters squared over seconds, right? And so that is the exact same particle, but again, notice we used a different center to calculate our angular momentum. So, and I forgot to encode the direction here. So notice right-hand rule would still give us a negative angular momentum. So I should have a negative here and a negative here. So that's my mistake. So notice between the two answers, obviously, they're different. So is that a problem? Right, between those two, it's the same particle moving in the same exact way. We're just using a different coordinate system. So this is not a problem, right? So you can get different angular momentum calculations because, again, what's really important, if we go all the way back over here, what's really important is really change in L. That's really all we care about. If we go back to these examples, what really matters is the fact that particle 1, L is conserved, right? There's no net torque on the particle, which means its angular momentum, right? Delta L is 0. L is not changing, right? All these things are true, all of them, for every single particle, in fact. And so really, it's not as important as, the number itself is not as important as is this changing, and if it is, by how much. So let's do a few more examples here. Let me go back over here. Let me do 4. All right, so if we go to particle 4, we have an r vector like this. So let's call that r4. Notice, well, let's just set it up first, right? So L4 equals, so this is a 7 kilogram mass times, it's going 2 meters per second, times the distance is exactly 4, so 4 meters. And then we have sine of what angle? Well, in this case, these two vectors are off by 180 degrees. So this would be sine of 180. But the problem is, what is sine of 180? It's 0, right? So actually the angular momentum of particle 4, in this case, is 0. It's exactly 0. So we could say 0 kilograms times meter squared per second. Right. Let's do the same thing we did last time. Let's mosey on over here. Notice where particle 4 is in this case. All right, so here's particle 4. Let's calculate the angular momentum here according to this center. All right, so that's my new position vector. I'm moving 2 meters per second, 7 kilograms. I guess let me keep the colors the same. So this would be L4 equals 7 kilograms, 2 meters per second. Let's see. And then think about the trick that we did with that orange triangle earlier. Same sort of thing is going to happen here, right? So I have this orange triangle. This is my, let's call this theta 4, right? Basically, right, R4 times theta 4 is going to give me this distance of 2. Right? So I would get 2 meters. And that, that trick, if you think about it, really just comes all the way back to this example, right? So if angular momentum is conserved, basically you can use the angular momentum of like the 90-degree angle case, and that's going to be the same as the angular momentum for all the other cases, like over here and over here, right? So that has to be true. If it's not changing, then we can use basically the velocity and the position vectors when they're at 90-degree angles. So that's essentially what we're doing here, right? We're using this position vector of length 2, and then the velocity vector, right? So in this case, we get a non-zero value. And, oh, I keep forgetting this. Right-hand rule would tell us, is this positive or negative? Again, put your fingers along R4, curl them towards the velocity vector, or which direction the velocity is pointing. My thumb is going into the page, so that's a negative angular momentum. So here, I get an answer of negative 28 kilograms meters squared per second. So again, notice, right, answers are different, but again, all that matters is it changing and how much. We can still calculate these numbers, and that's interesting. But sometimes it's not as useful, right? Or I guess what I'm trying to point out to y'all is sometimes it's more about where you put your center so that you can make your answers as easy to work with as possible, namely 0, right? Like we could put our center here and get this as our answer, but because we get to choose, it might just be better to put your center, for situations like this, wherever is most convenient, right? So if we put it here, we're getting a really nice answer for this fourth angular momentum. And so I know I have some other examples on here. I'll just leave you guys to do the rest of these if you want, just to sort of have some practice. But I want to save time so this video isn't too long. And maybe go over what kind of collision problems can you expect with angular momentum. Right, so this is an example of a kind of collision between two objects. In this case, we have what we would call an inelastic collision, right? So you're running towards this is like a merry-go-round, which is already spinning, right? It's got some angular velocity. And then you jump on it, or better yet, maybe don't even think of jumping, because jumping is going to affect the system here. Just think of yourself as this is like happening in space, and you're gliding at this velocity. And the moment you see the edge of the merry-go-round, you're going to basically just grab onto it with your hands. So maybe, better yet, I should draw this guy more like this. So he's hanging on, right? So I'm only saying this is in space, namely to point out that there's essentially no friction, no air resistance, and that's going to make doing this problem a lot easier, right? So that's super crucial that there's no friction or air resistance. So the first question, and our goal eventually will be to work towards, is there some kind of formula for how fast the system is going to rotate once you're hanging on to it? But the first question you should always ask yourself for momentum problems is my momentum quantity conserved? And you might want to take a second to think about it before I reveal the answer. So take a second and keep in mind, right, my system. I haven't defined the system yet, so that's my bad. Is the man plus the merry-go-round. Right, that is my system. Is L of the system conserved? I should have been more specific here. Okay, so what implies that L is conserved? Right? What thing has to be true? It's all about the net torque, right? What is the net torque on the system? Are there any torques acting on either the man or the merry-go-round from outside of the system? And the answer is basically no, right? If there's no friction, no air resistance, there's nothing I can think of that is torquing the merry-go-round or the man, which means net torque is 0, which means L of the system is conserved, right? So that's huge, right? So essentially, what we can do is we can say delta L equals 0, which also implies initial momentum of the system should equal the final momentum of the system. And this is where we start using some actual equations here. So what is the best equation to use, right? Because you guys actually learned, let's see, where are they? Where are those equations? Okay. You guys now know 2 totally different ways to calculate angular momentum, right? So this is where things get a little strange, because notice I'm dealing with sort of 2 objects. The man is basically a point particle, but the merry-go-round is what we would call an extended object. And for extended objects, you definitely want to use rotational inertia somehow, right? Because the mass is uniformly distributed, it's more complicated to work with. And so what I have over here is, this is the rotational inertia formula for the merry-go-round. You might remember this formula from sometime last semester when we talked about torque, right? This is for solid disks. We're treating the merry-go-round as a solid disk. You do not need to memorize, right? So if you ever have to use any of these formulas, they're going to be given to you. You're not expected to memorize them. They used to force AP Physics students to memorize them, and now they don't. So the initial momentum of the system is going to be the initial angular momentum of the man. Let's put comma I, plus the initial angular momentum of the merry-go-round, comma I. And that should equal angular momentum of the man final plus angular momentum of the merry-go-round final. All right. So let's do these one at a time. Angular momentum of the man, right? So if he's a point particle, we probably want to use mvr sine of theta, right? And keep in mind, you could calculate the angular momentum of when he's here, right? That r vector, here's your theta. But remember, if it's conserved, if he's not touching anything until he gets to the very edge of this merry-go-round, you could essentially say that it's going to be the same calculation as when he's here, right? So same velocity, but now he's exactly a distance capital R, the actual radius of the merry-go-round. So really, his angular momentum is mass v capital R. Is this a negative or positive angular momentum? Again, use right-hand rule. Looks like it's negative, right? So he's sort of moving clockwise according to our center of rotation. Right, so this is a negative quantity. If we go to the merry-go-round, right, so over here, we use the mvr sine of theta formula for this guy. We're going to want to use the I omega formula for the merry-go-round because it's an extended object, right? And in this case, merry-go-round is going counterclockwise, so that's a positive quantity. And it would just be I of the merry-go-round. We could put I merry times omega initial, right? That's what it was termed as. And luckily enough for us, we have this nice little formula for I of the merry-go-round. Let's go ahead and put that in here. Right, so I'm actually going to erase this. 1/2 capital M capital R squared. Now that should equal the angular momentum of the man final plus the angular momentum of the merry-go-round final. So this is where things get a little weird. We actually want to recombine these, right, into just angular momentum of the whole thing final, because it's actually easier to calculate it when you think of it that way. Once the man is now on the merry-go-round and they're both rotating with some final angular velocity, think about I, right? So I was defined as the sum of each little piece of mass times its respective radius squared. All right, so it stands to reason if you think about what this means, right? If we're talking about I of the system, we could split up this sum into just I of the man plus I of the merry-go-round. If we add up those rotational inertias, we get the rotational inertia of the system. Well, we have a formula for this one. And then what would I of the man be? It would be his mass, because we're treating him as a point particle, times capital R squared. And then this one over here would just be the formula that we already know. 1/2 capital M capital R squared. So this right here is the rotational inertia of the man merry-go-round system. Man merry system. Or the merry man system. It's very happy. So going all the way back over here, we could just write this as I of the system times omega final. And we just figured out what that is, right? That's M capital R squared. Let's see, plus 1/2 capital M capital R squared times omega final. And you might be wondering, do we know if this is negative or positive? We actually don't, right? We actually have no idea which direction this thing is going to rotate, because it really all depends on how heavy this man is, how heavy the merry-go-round is, how fast the merry-go-round was moving. It could have been moving almost 0 miles per hour, right? The man could have been moving at lightning speed. We just don't really know a whole lot of things. So all we can do at this point is just solve for omega final. And so that's what we're going to do. We're going to find, guess what? You've seen this before. Functional dependence. Dun, 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 dun. Right? So let's solve for omega final. So it's going to look a little complicated, but just divide both sides by this parentheses here. We get 1/2 capital M capital R squared omega initial minus MV capital R divided by, let me put the second term in front here, 1/2 capital M capital R squared plus M R squared. I'm just rearranging the terms because I like this order a little bit better. And I also want to simplify this a little bit. I notice I can do some stuff to the top and bottom here. So let's put some parentheses. And let me go ahead and multiply top and bottom by 2. And let me also do this. Let me multiply by 1 over R squared over 1 over R squared. Right? Because I notice I have a lot of R squareds here that I can sort of get rid of. This one's going to be a little messy, but it should make our life overall easier and should be easier to understand this equation once we do these two things. Right? So I'm doing the 2 to get rid of the fractions. I'm doing the 1 over the R squared to get rid of a lot of these R values. So omega final, if you do all this, I'm skipping a lot of algebra here, so you gotta follow my steps. But it looks like I get capital M omega I minus little m v over capital R. Oh, and there's times 2. Right, so I almost forgot that. Divided by capital M. And the next one would be plus 2 little m. So isn't that a lot nicer to look at? I think it is. Right, so this is our functional dependence. Right, it looks very complicated. Let's at least see if it at least makes sense with our intuition. So let's suppose the mass of the man is approximately 0, right? If you think back to what you would expect to happen, imagine the mass of the man is like a grain of sand moving at some speed, and it lands on this merry-go-round right here. Intuitively, we know that the merry-go-round will basically keep almost the exact same angular velocity. It's just going to keep going on its merry way. Right? That grain of sand is barely going to affect it. So if the mass of the man is approximately 0, then we should expect the final angular velocity to be the same as the initial, right? So let's go ahead and plug that in. Right, we would get minus 0 over big M plus 0. Well, notice big M omega I over big M, which is omega I, right? So that matches our intuition, right? Now let's suppose, this one's a little more outlandish, that the mass of the merry-go-round is approximately 0, right? So again, what would we intuitively expect to happen if the merry-go-round was almost weightless? Well, what would happen is essentially this guy would grab on hold, or would be holding on to this merry-go-round, but it's so light that basically it has applied almost a non-existent impulse to the man. So this man should still have the same tangential velocity, which would be, whatever angular velocity he had before times r. So, if we go back over here, right, angular velocity is velocity divided by r, right? So that would mean that v equals omega times r. All right, so let's just see if this matches our intuition. Omega times r. So go all the way down here. If the mass of the merry-go-round is approximately 0, what is the final angular speed of this thing? We get 0, we get minus 2 little m v over capital R, 0 plus 2 little m. And check this out. Wouldn't you know it? We get negative 2 mv over 2m capital R. Well, this is negative v over r, which is essentially, right, v over r would be the man's angular velocity right before he lands on the merry-go-round, which is exactly what we would expect. And it's negative because, if you think about it, right, if the man is moving in this sort of clockwise fashion around the center, then it's a negative angular velocity, which is why the answer is negative, right? So this is negative omega of the man. So that's cool. I think that's super cool. It matches our intuition, and for different masses, for the different objects, we would get different answers too, but this is the functional dependence. This is what really reveals everything to us. So I'm going to go ahead and stop right there. So as far as homework goes, right, you have AP Classroom problems. Don't forget to do those. All right, so that's one thing. Second thing is, I assigned this actually yesterday, the day before this async day, but you guys have a pivot lab, which is all about rotational, I guess it's called rotational momentum, something like that. Essentially, the setup is there's a rod, has a pivot here, and you're shooting a dart at it. So the dart flies over with some velocity. It hits the stick, and then they both are stuck together, and they start to rotate. And you just answer a bunch of questions about the angular momentum of the dart, the angular momentum of the rod. Key thing I want to point out here is you need a formula for this that they do not provide, which is the rotational inertia of the rod. So I'll just give that to you. You need this for the lab. Please do not, hopefully you did not turn off this video before seeing this. 1/12 capital M, so this is the mass of the rod, and then L is the length of the rod. There are literally questions where if you don't know this formula, you're going to be stuck for hours. So please, if you have a friend who didn't watch this video to the end, let them know, right? They need this formula. Otherwise, they're going to be stuck for like 2 hours not knowing what to do. You need that formula. And just as a little last minute fun fact, right? What's the deal with all these formulas? I don't know if I showed y'all where they come from. You don't need to know this, but I just think it's kind of fun because I love calculus. It comes from calculus, right? So if you're in A, B, or BC, you can actually derive these formulas all on your own. Essentially, the idea is this right here is kind of the same as that sigma mi ri squared thing, except you use integrals, right? So if you know what an integral is, should make some sense, right? Sigma and integrals are kind of both doing similar things. So this is for the hoop. It's a very simple formula. let's see, over here, I did one for the disk, right? That's the 1/2 mr squared. That's the merry-go-round one, right? I did not finish this one. I think I got the wrong answer here. But wouldn't you know it, for the rod, right? Specifically spinning about its middle part, there's that 1/12 ml squared. So if you like calculus, you might like this. If you don't know anything about calculus, just ignore everything I said and move on with your life. You don't need to know it. You do need to know angular momentum, right? You need to know this stuff. So hopefully that was some pretty good practice. And next time I see you guys, we should have just some really solid textbook practice lined up here. And then I can post all these good notes into the drive. So that'd be awesome. See y'all then. Make sure to do your homework. Stay safe.